think this really should be the shortest video ever in this series. So this is before worksheet 7, and it's going to cover Missouri's chapter 7. And the file name for these slides is in the files area. It's phys8 slides 07.pdf. So I think if this video will certainly cover the two equations you need to know from chapter 7. There are some concepts in Missouri's chapter 7 about interactions and types of interactions and the fundamental forces in nature and transformation of energy between different forms and dissipation of coherent energy to incoherent energy that I won't really do such a good job at. You won't really need them for problem solving, but if you do have time after going through this quick video to just skim through the concepts part of chapter 7 and kind of look at what he says, especially about transformation of energy from coherent to incoherent forms and source energy and energy diagrams, that could be useful, but it's not mandatory. Okay, and again, chapter 7, like chapter 6, is here mainly to prepare your mind and your intuition for the concept of forces, which will be introduced in chapter 8 and then used throughout the rest of the course. So there are really only two equations worth knowing from chapter 7. One of them is that when two objects interact only with one another, what does that mean? That means that the two objects form an isolated system. And we're only looking at the x-axis. So what we really mean, if you want to be precise, is that the system is isolated along the x-axis, which means that the only interaction in the x direction for each object is with the other object. Because if you took physics before and you know about gravity and you know about the upward force exerted by the floor on an object which is sitting on the floor, you might have been a little skeptical of this idea that there are no external pushes or pulls whatsoever. But when we've said that it's true on the x-axis, it has been true indeed on the x-axis. So you can suspend your disbelief for another chapter or two. So then the acceleration in the x direction of object 1 divided by the acceleration in the x direction of object 2 is just minus m2 over m1. And where on earth does that come from? Well, if objects 1 and 2 form an isolated system, at least as far as the x component goes, then you know that the total momentum of the 1-2 system stays constant. So then that tells you that if the momentum of object 1 in the x direction changes, then the momentum of object 2 in the x direction must change in the opposite way, such that the sum of P1 and P2 stays constant. And this would be the change in m1 v1x, and so that should be minus the change in m2 v2x. And then if the mass is a constant, then you have m1 delta v1x equals minus m2 delta v2x. And we can divide by delta t if you want to do this in some little unit of time. And then that gives us, so dv by dt, if you take the limit that delta t becomes infinitesimal, then that tells you m1 a1x, since you have a1x is dv1x by dt, and you have a2x is dv2x by dt. So we just let the deltas become d's as we go to the infinitesimal limit. So you have m1 a1x equals minus m2 a2x. So then you can say, aha, a1x over a2x is just minus m2 over m1. So that leads us directly to this key result. So that says if two objects are pushing only on each other, and there isn't anything outside that two-object system pushing or pulling on either object, then if they push against each other, then they both recoil from one another, and the less massive object will accelerate more, the more massive object will accelerate less, and the ratio of their accelerations is just minus the reciprocal of the ratio of their masses. The minus sign is because if we're pushing on each other, if I accelerate to the right, then you will accelerate to the left, and vice versa. And the reciprocal is because the more massive object gets a smaller acceleration in magnitude, and the less massive object gets the larger acceleration in magnitude. So this will turn out to be deeply connected to Newton's third law when we get to forces in chapter 8. Okay, so that's one thing, and I have a little video clip with myself recoiling from throwing a medicine ball, which you will see on the next slide. So the other key result, quantitative result from chapter 7, is if I pick up a ball from, let's say, the ground. So let's say here's my x-axis in this funny convention that we use for the first 9 chapters of Missouri, where we only call the variable x. So if I have, in the initial state, I have a basketball here on the ground, and it has mass m, and we'll call this x equals 0. And then in the final state, I have lifted this ball up to some height x equals h. So basically lifted it up to this height. Then I have added, if I lift an object of mass m from an initial height x equals 0 to a final height x equals h, then I increase the gravitational potential energy of the Earth plus object system. So the system which contains, basically the system which contains both the ball and Earth. Actually, it turns out if I'm going to talk about gravitational potential energy, then Earth has to be part of the system. And you can look through the chapter to see why. By a change, so I can say U equals mgh, okay? So if I started off at x equals 0. So I didn't want to assume when I wrote this equation down that you necessarily started off at x equals 0, so I could say, well, the change, oh, by the way, I usually put a g here for gravitational. The change in the gravitational potential energy is mg delta x, okay? And the really important thing to keep in mind is that gravitational potential energy is something that you associate with the relative positions of several objects. So the ball by itself cannot have gravitational potential energy. The system consisting of the ball and Earth can have gravitational potential energy. And if I move the ball delta x farther away from the center of Earth, then I increase the gravitational potential energy of the ball plus Earth system by mg delta x. So if I go from x equals 0 to x equals h, I have increased the gravitational potential energy of that ball plus Earth system by mgh. A little bit tricky, but it's going to be very useful, because then we can go back to our favorite example of the basketball, and we'll see how we convert back and forth between mgh and 1/2 mv squared. So we'll see, you lift up the basketball to a height h. Now all the energy is in the form of gravitational potential energy. You release it, It goes faster and faster and faster as it approaches the floor. Just before it hits the floor, it has kinetic energy, 1/2 mv squared, and it has lost this mgh. This mgh has been transformed into 1/2 mv squared. Then it bounces, and a little bit of that kinetic energy is lost it's dissipated into thermal energy because the collision with the ground is not perfectly elastic. But anyway, so now you have another 1/2 mv squared where that v is a little bit smaller. V is reduced by a factor of the restitution coefficient between the ball and the ground. And then it goes back up, and the kinetic energy goes down, and the gravitational potential energy goes up, and you reach some height mgh, where the new h is smaller than the original h. Actually, kind of a tricky fact if you want to think about this. The new h is a factor of the restitution coefficient squared times the original h. See if you can think about that. That's pretty tricky, but it's because v gets multiplied by the restitution coefficient, so h must get multiplied by the square of that restitution coefficient. Okay, so those are the two equations we're going to use from Chapter 7. Other than that, there is a discussion of kinds of interactions and how energy can be transformed, and the idea that there's source energy. For example, when the women on ice skates threw the snowball, there was some kind of source energy coming from the kind of food calories stored in her body, which her muscles then can transform into kinetic energy. So a battery or muscles or so on represent some kind of source energy, and then energy can sometimes, so that can become useful mechanical energy. So this is like, how do you take stored fuel and convert it into useful mechanical energy? So Mazur's book denotes that as source energy, which might be from a battery, it might be from a chemical fuel, it might be from food, and so on. And then energy, you say, well, energy often, eventually, from mechanical form gets transformed into some disorganized state, which is just, often it's heat. So there's some discussion of going from coherent form to incoherent form. So all of the molecules of the ball moving up or down together versus the ball just heating up. If the ball just heats up, then you've got all the molecules of the ball just jiggling back and forth in random directions a little bit faster. That's a little bit of a tricky concept. Okay, so again, result 1 from Chapter 7, a1x over a2x is minus m2 over m1. This is if two objects interact only with one another, and their interaction is along the x-axis. And I will show you now a video clip where the medicine ball is, in US customary units, the medicine ball is about 15 pounds, and I am about 150 pounds. Medicine ball is actually a little less than 15 pounds. I'm a little more than 150 pounds. So there's basically like an 11-to-1 ratio of my mass to the medicine ball's mass. So it's a little more than 10-to-1. So you'll see when I push the medicine ball away from me, I recoil back. And if you could look at the acceleration or the rate of change of velocity of the medicine ball, it should be about 10 times as large as the recoil of me in the opposite direction. So you can see, if you can see that in the video clip. And you say, to make this work, I have to be interacting with the medicine ball, and I have to be interacting not with anything else, so I stand on a skateboard. So I stand on a skateboard so that in the horizontal coordinate, I am not interacting with the floor, I'm only interacting with the medicine ball. So you see me throw the medicine ball, and you see me recoil, and you see that my change in velocity is basically about 1/10 and in the opposite direction from the medicine ball's change in velocity. And then if you were to look microscopically frame by frame, infinitesimally frame by frame rather, then you would see that my acceleration is about 1/10 and in the opposite direction. So it's about minus 1/10 of the medicine ball's acceleration. So let's see if we can see that.
That was pretty good.
So again, the second key quantitative result from chapter 7 is that if you lift an object up by a change in height delta x, so let's say here's x initial and here's x final, and let's say the difference in height between x final and x initial is delta x, so delta x is x final minus x initial, then the change in gravitational potential energy of the object plus Earth system, like this is a ball usually for me, so that's u gravitational final minus u gravitational initial. So we're only talking about changes in potential energy, and you could usually define wherever is convenient for the point where the potential energy is taken by convention to be zero. Often we say x equals 0 is where the potential energy equals 0, but it's just a convention. So the change in gravitational potential energy is mg times the change in altitude. So if x initial is 0, which is convenient, and if you take the gravitational potential energy to be 0 when x equals 0, which is convenient, and if x final is h, so we could say that this is x equals 0 down here, and this is x equals h up here, then more simply you say u gravitational in the final state up here is mgh. That's the way I usually remember it. I usually say that the gravitational potential energy of the Earth plus ball system is mgh, where h is the height above the ground. That is the easiest way to remember it. So now I'll show you a little video clip where I lift up a ball and then I let the ball bounce, and we'll see the transformation back and forth between gravitational potential energy up here and kinetic energy down here.
If I lift the ball up, then I increase the potential energy of the Earth ball system by m times g times h, where h is the altitude gain of the ball from its low point to its high point. And then the ball can give back that potential energy when I drop it. But of course the medicine ball doesn't really bounce, so all of that gravitational potential energy in this case is converted into thermal energy. It's just heating up the bottom of the ball. If it collided elastically with the floor, then it would recoil upward at the same speed at which it had impacted downward. That's close, but not exactly true. The most direct measure to your eye of the amount of energy being lost by the ball on each bounce is how high the ball subsequently travels. So you can see, here I'll start the ball up here, and you'll see with each subsequent bounce, the maximum altitude's a little bit lower. And where is that loss of energy happening? That loss of energy is actually happening from just before the collision with the floor to just after the collision with the floor, because that collision is not perfectly elastic. So a little bit of that kinetic energy is converted into heat with each bounce, converted into thermal energy with each bounce.
Let's talk through a little example problem. So I release a 1 kilogram ball from rest from an initial height of x equals 5 meters above the ground. And let's use g as approximately 10 to keep the math easy. So what is the ball's initial, it's actually ball plus Earth system. I think I first wrote this slide before I got so good about reading Mazur's notation. So what is the ball plus Earth system initial gravitational potential energy? You cannot really say the ball alone has gravitational potential energy. You have to say the ball plus Earth system has gravitational potential energy. Pardon me. So what is the ball plus Earth system initial gravitational potential energy? Let's define x equals 0 to be where the gravitational potential energy equals 0. So we have x initial equals plus 5 meters, and we have the x-axis pointing up. And so I would say the initial gravitational potential energy is mg x initial, because we're taking x equals 0 to be where u gravitational equals 0, and that is 1 kilogram times 9.8, well, I'll write 9.8 even though I'm going to use 10, 9.8 meters per second squared times 5 meters, which is approximately, there's 10 times 5 is 50 joules, okay? So energy, the unit of energy is a joule. So initially we have 50 joules of gravitational potential energy stored in that Earth plus ball system. And what is the ball's initial kinetic energy? So I think initially, so in this initial state, which I guess would have like a little clock near 12 o'clock in Mazur's book, we have, here's the ground, and the ball is up here, and it is not moving. And I can't remember how you say it's not moving. I guess we have a little dot there to say it's not moving. Okay, so I would say this is A. So this is U gravitational is 50 joules. That was A. B, what is the ball's initial KE? It's 0 because its initial speed is 0. It's not moving. So the answer for B, I would say, is 0. What is the ball's, actually ball plus Earth system's gravitational potential energy immediately before it reaches the ground? So I'm going to say, okay, so it's immediately before it reaches the ground. We can say at some later time, which I guess our textbook would represent with a little clock like that. Then it seems like the ball now is just above the ground, and it's like it has a big velocity downward, but it's basically at x approximately equal to 0. So in that case, we have U gravitational basically equals 0 joules, because the height is 0. So the height has gone from 5 meters to 0. So that's 0 joules of gravitational potential energy in the Earth ball system, taking the ball's height immediately before it hits the ground to be 0, and taking 0 to be the value of gravitational potential energy when the height is 0. And there, you can choose your own convention for the offset, it turns out, with potential energy. What is the ball's kinetic energy immediately before it reaches the ground? Aha! Well, you see, this is where the closed system concept and the fact that energy is a conserved quantity is so handy. So we can use energy directly to work this out. And we say, well, you see, all of this initial state gravitational potential energy got converted into kinetic energy. So in that case, we have, so this is x final is 0. So we have U gravitational final is 0, but we have kinetic energy final is 1/2 mv final squared, and that should be 50 joules. So I claim that all of that initial gravitational potential energy was converted into kinetic energy by the time the ball is just about to reach the ground. And we could check that. Actually, I think we will check that. So what is the ball's KE immediately before it reaches the ground? I would say K equals 50 joules. What is the ball's speed immediately before it reaches the ground? We could use this to get the speed. I think we will, but let me just show you a different way to do it. You know it was accelerating downward at a sub x equals g. So you know Vx final squared equals Vx initial squared plus 2 a sub x, x final minus x initial. This gives you Vx final squared. So it started out at a speed of 0, And then, actually, this isn't plus, this ends up, well, okay, this is plus 2 times, and then this is minus g, and then x final is 0, and the x initial was h, or well, it's called x initial. So this equals 2g x initial. So that's 2 times 10 times 5, right? So 2 times 9.8 times 5 meters. So 2 times 10 times 5 is 200 times 5 is 1,000. 2 times 10 is 20. No, 100. So that's 100 meters squared per second squared. And then that gives us Vx final. This is, I guess we'll say the velocity is minus 10 meters per second. Okay, so its speed is 10 meters per second. It's 10 meters per second downward. So Vx final is minus 10 meters per second. So actually, I guess I found its velocity. Its speed is 10 meters per second. Its velocity is minus 10 meters per second in the x direction. Let's see if that's compatible with this number. So if we take 1/2 mvx final squared, we get 1/2 times 1 kilogram times 10 meters per second. That's really minus, but the minus goes away when you square it. So that is 1, says 10 times 10 is 100, times 1 is 100, times 1/2 is 50. That's 50 joules. So that checks out, okay? So that tells you that the kinetic energy computed using the fact that it's accelerating downward at g is the same as the kinetic energy that we computed using that the transformation of initial state gravitational potential energy was then completely into the form of final state kinetic energy. So the initial GPE translated into, final KE. So the answer is 10 meters per second. If you wanted the velocity, it would be 10 meters per second downward, but the speed is 10 meters per second. If the ball bounces elastically off the floor, then there's no energy dissipated in the collision with the floor. So it goes from 10 meters per second downward just before it hits the floor to 10 meters per second upward just after it hits the floor. So then immediately after it bounces, it's going to be at the same x approximately equal to 0, but it's going to be going upward instead. So it has a lot of kinetic energy, and there's still no gravitational potential energy in this Earth ball system. And then if you look even a little bit later, then we'll see that the ball has reached this altitude where now it's not moving anymore. I mean, it's instantaneously at rest, so it's reached its maximum height. And so now we're back in the form of mgh. I'll just call this h, right? So I'll call this height h, I'll call this height 0. So we start out here with mgh, and then down here we don't have any mgh left, but we have some 1/2 mv squared, and then here we have 1/2 mv squared. It's the same kinetic energy, but the velocity is in the opposite direction. And then now we've transformed that 1/2 mv squared back into mgh when we get to the apex again. So it's this transformation back and forth between gravitational potential energy, kinetic energy, gravitational potential energy. And if you really stretch your mind a little bit, there's actually this instant while it's bouncing off the floor where there's actually some other kind of energy. It's like elastic energy because the ball has been squished. So the ball and the air inside the ball have been squished, and that's kind of like compressing a spring, and then the spring uncompresses. So that's, you might say, but let's not get into that. Okay, so I would say it'll reach the same height because if the system is closed and if the collision is elastic, then no energy escapes, And the transformation of energy into incoherent forms is negligible if we're saying the collision is elastic. So therefore, we will reach the original height of plus 5 meters. Now this last part is tricky. If instead the ball bounces off the floor with a restitution coefficient E equals 0.9, what height will it reach after bouncing? This is pretty tricky. Okay, so let's say step 1, we have x1 equals plus 5 meters, v sub x1, I'm going to say 1 instead of I here, equals 0. So then we have u1, which is gravitational, is mgx1 is 50 joules, and we have k1 equals 0 because it's not moving. Okay, so that's before I release the ball. It's up high. Now, step 2 is just before. So number 1 was up high, before release. Or maybe just after release, either way, like the instant that I release it. Then, just before bounce. Okay, so this is moment 2. We have x2 equals 0. We have vx2. Well, we worked out what that was. So that was minus 10 meters per second. And then we have u2, gravitational, is, so I'm saying 2 for instant number 2, because we're going to have 4 steps, I think. And this is mgx2 equals 0. And then we have k2, that's 1/2 mv squared, so this turns out to be 50 joules. Now, see, this is the fun part. Now we're going to say instant 3 is just after bouncing. Okay, just after bouncing, x2 is 0. So we have this is 3. Sorry, x3 equals 0. So we have u gravitational 3 is still 0. It's mg times 0 is 0. And then we have vx3. Well, it's upward, so it's some positive number, but it's not 10 meters per second. Now it's 9 meters per second because we have, this is, you see, it's vx3 is minus e times vx2. You see, so because the ball recoils off the floor. And you think of the floor as like an infinitely massive thing that the ball recoils with. So therefore, if the collision were elastic, the ball would simply flip the sign of its velocity in the vertical direction. But it's not quite elastic. It's a little bit inelastic. You have this restitution coefficient E equals 0.9. So that means Vx3 is only 90% of minus Vx2. If we're perfectly elastic, you'd have Vx3 is minus Vx2. Because it's a little bit inelastic, you have E equals 0.9, you only get Vx3 is minus 90% of Vx2. So Vx3 is plus 9 meters per second. That's kind of cool. And then, so you see all the energy loss happens with the floor because that's where energy gets turned into heat, or thermal energy. So then we have K3 is 1/2 mvx3 squared. So 9 times 9 is 81, divided by 2 is 40.5. So that's 40.5 joules. So then we say number 4, step 4 is up high at apex after first bounce. What do we get? We get, okay, the easiest way to do this is to say, well, where did the energy go? The energy just went into gravitational potential energy. So you know that at the apex, it's instantaneously at rest. So the kinetic energy is 0. So all of that kinetic energy, K3, must have transformed into gravitational potential energy. So we're going to say U for gravitational is mgx4 equals 40.5 joules, and therefore x4 equals 40.5 joules divided by 1 kilogram. I guess I'm using 10. I'm not using 9.8. I'm using 10. That's fine. Okay. 1 kilogram times 10 meters per second squared, which is 4.05 meters. Yeah. So we started out 5 meters in the air, and after bouncing, we got only 90% of the speed, but 90% of the speed actually is 81% of the kinetic energy. So you see, the speed got multiplied by a factor of 0.9, therefore the kinetic energy got multiplied by a factor of 0.81, and then you see that the final height is 81% of the initial height. So you have this 4.05 meters. This is x4 turns out to be e squared times x1. That's kind of cool because the restitution coefficient denotes the change in speed, and the change in kinetic energy is the square. The ratio of kinetic energies is the square of the ratio of speeds. The restitution coefficient refers to the ratio of speed after versus before colliding with the floor. And then, we started out in gravitational potential energy. That all got converted into Ke. And then there was the bounce off the floor where we lose about 20% of the Ke to thermal energy, and then that Ke after the bounce gets turned completely into GPE, but of course there's only 40.5 joules of GPE at this apex number 3 here, this apex number 4 here, whereas there was 50 joules of GPE at this apex number 1 here. See if you can puzzle that out. So I'm going to say the height it will reach after bouncing is plus 4.05 meters. Yeah. And this is all using G is approximately 10 meters per second squared to keep the math easy enough to do in our head. So see if you can puzzle that along with me. I think this is kind of fun and worthwhile. We'll do a couple of similar problems in class. Suppose your friend's mass is about 50 kilograms and she climbs up 30 flights of stairs. So that's about 100 meters. A flight of stairs is about 3 meters. To check out a great rooftop view of the city's architecture. Okay, so she started out at x equals 0 and she moved to x final equals 100 meters where the x-axis points upward in this problem. How many joules did climbing the stairs change her gravitational potential energy? So we'll just take x equals 0 to be u equals 0. So this is u gravitational initial. This is the friend plus Earth system. This is 0 joules. And then we have u gravitational final is, this is mg times x initial, so I took a shortcut, right? Because we have u gravitational is mgx. Okay, so this, and where x x means height. I really should say mgh. Okay, so this is mgx final. So this seems to be 50 kilograms times, so let's say 50 kilograms times, let's say 10 meters per second squared, and then times 100 meters. And that is, so 50 times 10 is 500 times 100 is 50,000, 50,000 joules, 50 kilojoules. Let's see if that's right. So 50, 500, 5,000, 50,000. Yeah, 50,000 joules, which is 50 kilojoules. Where did this gravitational potential energy, so I would say this is 50,000 joules, which is 50 kilojoules. Where did this gravitational potential energy come from? Aha! So you see, this is a concept you'll see if you skim through the energy diagrams in chapter 7. Then he has this concept of source energy. So source energy is like stored in a battery, stored in fuel, stored in food, and so on. So the source energy in this case was like, calories stored in her body. Okay, so like calories stored in fat, in muscle, and sugar in her body. So what source energy? I would call this, I would ultimately call it food energy, right? So let's just call it like food energy. Or you could call it like, whatever, like her metabolic reserve. Okay. How many food calories did she burn, assuming unrealistically, that one's muscles are 100% efficient at converting food into mechanical work? I think it turns out more to be like 20% efficient. So realistically, your metabolism or muscles are like roughly something like 20% efficient at turning stored food into mechanical work. Let's say it's 100%. Okay, so then 50 kilojoules. So by the way, one chemical calorie is 4.18 joules. One food calorie in the US, I'll say US, one US food calorie is 4.18 kilojoules. So I'll take 50 kilojoules times 4 point, that's not right, times 1 calorie, this is a food calorie, per 4.18 kilojoules, and that's like 50 divided by 4 is like 12, right? So let's say that's about, so that's something like 12 food calories. Did I do that right? So 12 times 4 would be 48. Yeah, that's about right. Okay, so yeah, about 12 food calories. So seems like she burned about 12 food calories climbing up 30 flights of stairs. Now, actually, your muscles are only about 20% efficient, so that really means that to do that amount of mechanical work, you would probably in real life burn more like 12 times 5. So to scale 20% up to 100%, that's times 5. So probably more like 60. So I think actually climbing 30 flights of stairs would probably burn more like 60 calories. But anyway, in the context of this problem, where we're pretending that her muscles are 100% efficient, we're saying it's a mere 12 food calories. I think if we more properly accounted for the inefficiency of muscles at converting stored food into work, it would actually be more like 60 food calories. But so anyway, you get it, right? So initially, she has a velocity of 0. But she has some energy stored in the form of metabolic energy in her body. Then she climbs up the stairs. She makes it to the top. At the top, her velocity is also 0. So there's no net change in kinetic energy. I mean, while she's going up the stairs, she has a small kinetic energy. It's pretty small. And she can go up the stairs as slowly as she likes. So initially, there is metabolic energy stored in her body, and there's 0 gravitational potential energy. Then she goes up the stairs, and she gets to the top, and there's gravitational potential energy, And meanwhile, the metabolic energy in her body, the source energy, is decreased by this 50 kilojoules. And the gravitational potential energy is increased by that 50 kilojoules. Now, the detail that we're overlooking is that in order to release 50 kilojoules, in order to convert food into 50 kilojoules of useful mechanical energy in the form of gravitational potential energy, she'll probably end up wasting something like 200 kilojoules, just turning it into heat, because you exercise, your body warms up, you sweat. So that's a detail we won't worry about in this problem. So let's pretend that her muscles are completely efficient. Then that 50 kilojoules of stored food energy gets converted into 50 kilojoules of gravitational potential energy by her muscles. If you want to sweat the details a little more, you could say, well, there's actually a side effect where 200 kilojoules of additional food energy get thrown away in the form of heating up the environment. So her total source energy actually decreases by, 250 kilojoules, which is more like 60 food calories. But we're not worrying about that detail in this problem. I just wanted to say there's actually more to the story if you want to be completely realistic. So if you want to be unrealistic, which we're doing in this problem, 50 kilojoules of initial state source energy, which is stored food calories, gets converted into 50 kilojoules of mechanical stored gravitational potential energy. At this point, the slides I usually show in class say begin digression, meaning this is not going to be really important to your problem solving, it's kind of for your understanding. So I think I showed you once before, so there's this kind of simple ball and spring model of the atoms in a solid. So you can think of the atoms in a solid as being kind of like a regularly spaced array, and then you can think of the little internal connections between the atoms in a solid as being like little springs connecting those little balls together. And in order to displace one of the little balls, you have to stretch one of the little springs, or several of the little springs. And then also you can even say, well, thermal energy is this kind of random jiggling back and forth of these molecules. So if you heat something up, then the molecules jiggle back and forth more quickly, but they still basically stay in the same place. And then you can squish a material, so things get squished together, or you can stretch a material, things stretch apart. And then there's this kind of interesting process where you can deform a material, where you kind of permanently dislocate parts of it. So maybe you somehow move this thing permanently over to here and it doesn't go back. So that would be an example of what Eric Mazur would call a dissipative or an incoherent process. If you kind of somehow you hit this thing with a hammer in such a way that you permanently displace some of the molecules in a kind of random way. So that would be an example of what his book, chapter 7, would call an incoherent conversion of coherent energy to incoherent energy, where if you squish everything nicely, and that's called coherent, because you can usually get it back. If you do something coherent, normally you can get it back. But if you do something incoherent, so that kind of moves in this kind of permanent way, you don't get it back. It's kind of like you're transforming the material internally. And then there's another way that you don't get it back. You can make the whole material as a whole move around. Like I can throw the ball across the room and catch it, and I get that back. But if I just make all of the atoms in this solid jiggle faster and faster, that is thermal energy, and it's in general difficult to turn thermal energy back into useful mechanical work. You can only do it under certain limited circumstances, and you can never do it with perfect efficiency. So that's also incoherent. Incoherent is like the random jiggling of molecules. So it's another kind of useful to keep a picture in your head of a solid material as like a regular lattice of atoms or molecules, and then there are these little spring-like connections between them, and then the little atoms or molecules are jiggling, and that's there's thermal energy, which is proportional to their temperature, and they're jiggling all in different ways, and then you can squish the material and unsquish it, and squish it and unsquish it. That is coherent, and it's like a spring-like phenomenon, and you get the energy back when you release it. Whereas if you heat something up, generally that like I could throw something against the wall, and I have this nice coherent 1/2 mv squared, and then it turns into this kind of incoherent mess of a whole bunch of tiny little 1/2 mv squareds that are all in different directions. And you generally can't get that back into coherent form. So chapter 7 has this discussion of transformation of energy from source energy into useful mechanical energy, and then finally dissipated into incoherent energy, which is not in a useful form. So I have a little model of a bunch of marbles on an egg crate, which I will show you in the next video clip, which kind of illustrate an irreversible versus a reversible deformation. So elastic collisions involve purely reversible processes. So if you squish something, you can unsquish it, so you get that back. So it is reversible. And actually, reversible means that if you deform the material, you deform it in a coherent way. All the pieces kind of deform in a simple way with respect to one another. Whereas an irreversible deformation is a conversion that you cannot undo, so then it results in an inelastic collision or even a totally inelastic collision, and it's not reversible. You'll play the movie backward, it doesn't make sense, because it's something that doesn't just spontaneously undo itself. And so I have a little illustration with my little marbles on an egg crate of how that looks microscopically. So irreversible processes tend to correspond to the transformation of energy in coherent forms into incoherent forms. And that is generally called a dissipative process, where you have this kind of coherent energy being dissipated into incoherent jiggling.
So when we were talking about collisions a week or two ago, we noted that a perfectly elastic collision, if played backwards with the video camera, would still look in reverse motion like a perfectly elastic collision. So in fact, if all of the interactions are elastic, then if it looks like good physics to play the movie forward, it will also look like good physics to play the movie backward. Where by contrast, if you have some kind of energy dissipation mechanism, then your mind's eye can tell pretty obviously whether the movie is being played backward or not, because it doesn't make sense for things spontaneously to gain energy, for energy to be, basically undissipated. So elastic collisions are an example of a reversible process. And inelastic collisions are an example of an irreversible process. And in general, anytime we have kinetic energy or potential energy dissipated into other forms, and into thermal energy, or sometimes dissipated into incoherent rearrangement of a system, then that is known as an irreversible interaction. So dissipative processes and things that cause the constituents of a whole to move in incoherent ways versus coherent ways. So here's an example of a coherent motion. I can move this crate as a whole coherently in one direction or another. And what is this crate? So most solids, and especially, for example, a metal like a block of steel or many inorganic compounds, consist of a regular lattice of atoms. So atoms are spaced in some kind of a regular pattern. It doesn't have to be a perfectly rectangular pattern like this, but it is a regular repeating array. And so you can imagine each one of these orange marbles playing the role of one atom in my solid. And then this egg crate sort of represents the electrical interactions that they're basically interactions between the atoms that hold each atom in place in the solid so that they don't move with respect to one another. And if I move the entire block of steel around, then I'm moving all of the atoms coherently like this. So they're all moving together. By contrast, if I heat up the solid, then I'm causing each atom and also the related electrons to jiggle a little bit. So it's not moving far away from its, each atom, say, is not moving far away from its normal location, but is sort of jiggling around. Similarly, we said when you have a totally inelastic collision, then somehow you are incoherently deforming the atoms in the object. So you imagine a car crash between two cars, and at the end, the kinetic energy has been transformed into other forms, and some of it might be heat because you've warmed up the metal, so then you have the atoms jiggling, and then some of it might be, kind of the irreversible bending of parts of the metal. And one way to model that is to say, well, if I move each atom just a short distance from its normal home, then it will go back. So I can move each atom within the array, within the lattice, like let's say just a little bit. If I don't move it too far, then the elastic nature of the material, which we'll study more when we start to talk about materials out of which architectural structures are built. So these forces will bring the atom back to its initial position. But if I push it too far, then it deforms into some other location. So, and I could do this in a way that's maybe a little bit different for the different atoms of the solid. And now I've deformed this solid in an incoherent way. And this is an irreversible interaction. So there's a sort of connection between, so anytime you have a dissipative process in which things are, in which initial energy, coherent energy in the form of kinetic energy or in the form of potential energy is transformed either into thermal energy, which is the incoherent random back and forth jiggling of atoms and of electrons, or the incoherent rearrangement of the atoms from their ordinary locations to some displaced locations. That's an irreversible process. So that's a process for which if you played the movie backwards, your eye could tell that it's not sensible physics, that it doesn't make sense. If you watch a movie of a car crash played backwards, you know that that would never happen forward. So you know when you're watching a movie of a car crash played backwards, that it's being played backwards. By contrast, if you watch a movie of, let's say, a golf ball bouncing off of the ground, and you watch the movie backwards, it would be difficult for you to tell whether the movie is playing forward or backwards. Maybe the easiest way for you to tell without carefully measuring the velocities before and after would be if you see how high the golf ball was dropped from, and you could see that it reached a slightly less high altitude when after the collision. But if you don't look too closely, it'd be pretty hard for your eye to tell whether the movie of a golf ball colliding with a nice smooth surface is played forward or played backwards. So that's an elastic collision, and it's a coherent interaction. So, and it's reversible. So there's this sort of picture maybe to keep in your mind's eye that dissipation of kinetic energy and potential energy into incoherent forms usually involves incoherent motion of the atoms of a solid with respect to each other, or an irreversible incoherent deformation of the material. I also showed you once before my extremely low-tech animation of two objects in a totally inelastic collision, where what starts out as nice coherent energy gets converted into this kind of incoherent jiggling. I'll quickly show it to you again just for fun.
And then finally, even more fun is this video, a high-speed movie of the it's almost completely elastic. It's not quite, but it's surprisingly close to elastic. This is a golf ball bouncing off of a wall at 150 miles per hour, which is what? That's like probably roughly 250 kilometers per hour. So here, I'll show you this clip also. And then end of digression and end of lecture. So this should be the shortest one yet.